Welcome! In this video, we'll dive into LeetCode problem number 2179, titled Count Good Triplets in an Array. Together, we'll explore the problem requirements and develop an efficient solution. Let's get started. In this problem, we are tasked with determining the number of good triplets in two integer arrays nums1 and nums2 of the same length n. Here, nums2 is a permutation of nums1, meaning it contains the same elements, just possibly in a different order. A triplet is defined by three distinct indices, I, j, k, where I is less than j, and j is less than k. For the triplet to be considered good, the relative order of the values at these indices in nums1 must match the relative order of the corresponding values in nums2. Our goal is to compute the total number of good triplets. The input consists of two arrays, each of length n, where n can be as large as 100,000. The output is a single integer representing the count of good triplets. To solve this problem efficiently, we need to consider the constraints and ensure our solution performs better than a brute force approach with time complexity of n cubed. Let's look at an example to better understand the problem. Suppose nums1 is 2, 0, 1, 3, and nums2 is 0, 1, 2, 3. The output in this case is 1, because there is only one good triplet, 0, 2, 3. To verify, we observe that in nums1, the elements at these indices are 2, 1, and 3. In nums2, the elements at the same indices are also 2, 1, and 3. The relative order is preserved, as 2 comes before 1, and 1 comes before 3 in both arrays. This satisfies the conditions for a good triplet. No other combinations of indices from nums1 and nums2 meet the criteria, so the total count is 1. Now, consider another example where nums1 is 4, 0, 1, 3, 2, and nums2 is 0, 4, 3, 1, 2. This time, the output is 4, as there are 4 good triplets. These are 0, 3, 4, 1, 3, 4, 0, 2, 4, and again 0, 3, 4. In each case, if we check the relative order of the elements at these indices in both arrays, it matches. For example, 4, 0, 3, 4, the values in nums1 are 4, 1, and 2, and in nums2 they are 4, 1, and 2. The relative order is consistent. Similarly, the other triplets also satisfy the condition. However, given the constraints, we need to ensure our approach is efficient, as directly iterating through all possible combinations to check for good triplets would be computationally expensive for large values of n. Finally, let's discuss some edge cases. If the input arrays are very small, such as when n equals 1, there are no triplets to consider, so the result is 0. If the two arrays are identical, meaning nums1 is exactly the same as nums2, then every combination of indices forms a good triplet, and the total count would be the number of ways to choose 3 indices from n, which is given by nc3. On the other hand, if nums2 is the reverse of nums1, no triplet can satisfy the condition, so the output would be 0. For large inputs, such as when n equals 100,000, our solution must be highly optimized to avoid excessive computation time. An efficient algorithm is critical to handle these scenarios within the given constraints. To tackle problem number 2179, we need to identify all valid triplets, I, j, k, from two arrays, nums1 and nums2, while adhering to the constraints given in the problem. One straightforward way to approach this is through brute force. Here, we iterate through all possible combinations of indices I, j, and k such that I less than j less than k, and check if they satisfy the problem's constraints. Since nums2 is a permutation of nums1, it's easy to map indices between the two arrays. However, this method involves 3 nested loops to evaluate all triplet combinations, resulting in a time complexity of n cubed. While the brute force approach is simple to understand and implement, it becomes computationally expensive for larger arrays due to the sheer number of iterations required, making it impractical for large inputs. The inefficiency of the brute force method leads us to consider optimized strategies. A key observation here is that the relative order of indices in nums2 determines whether a triplet is valid. By mapping values from nums1 to their corresponding indices in nums2, we can simplify the problem to finding triplets that satisfy the condition I less than j less than k in the order of nums2. This is where the Fenwick tree, or binary index tree, bit, comes into play. Using this data structure, we can efficiently maintain prefix sums to track and count indices that meet the constraints. The process involves iterating through nums1 while dynamically updating the Fenwick tree. For each element, we use the tree to perform range queries and count valid indices for I and j, which are then used to compute the number of good triplets. This optimization reduces the time complexity to O(n) log n, as the Fenwick tree supports both updates and queries in logarithmic time, making it far more efficient than a cubic solution. This optimized solution has several advantages. First, it scales much better for larger inputs compared to the brute force approach. Second, it leverages the structure of the problem by using a data structure that elegantly handles the required range queries and updates. As an alternative, we could also use a segment tree to achieve similar functionality. Like the Fenwick tree, the segment tree allows for efficient range queries and updates, with a time complexity of O(n) log n. However, a segment tree is more complex to implement and typically involves additional overhead. In contrast, Fenwick trees are simpler and faster for this type of problem. Given these trade-offs, the Fenwick tree emerges as the superior choice for its balance between simplicity and efficiency, making it more practical and easier to work with. The key insight that unlocks this problem is the realization that mapping nums1 to nums2 allows us to focus solely on index-based constraints. Using a Fenwick tree to maintain prefix sums enables efficient range queries, which is crucial for counting valid triplets without relying on nested loops. This drastically improves performance from O(n) cubed down to O(n) log n. When comparing approaches, the brute force method is simple but computationally prohibitive, while the segment tree offers similar complexity to the Fenwick tree but introduces unnecessary implementation complexity. The Fenwick tree strikes the ideal balance by being both efficient and relatively easy to implement, making it the best choice for solving this problem on large inputs effectively. To solve the problem of counting good triplets, we begin by understanding the input and output requirements. We are given two integer arrays, nums1 and nums2, both of length n. These arrays are permutations of the first n natural numbers. Our task is to count the number of triplets, I, j, k, where the indices satisfy I less than j less than k, and the relative ordering of the elements in nums1 matches the relative ordering of the corresponding elements in nums2. This means that the sequence of values at indices I, j, and k in nums1 must align in the same relative order as the sequence at the same indices in nums2. The key insight here is that the problem revolves around maintaining the relative order of these elements. Since nums1 and nums2 are permutations of the same values, we can simplify the task by mapping the indices of one array to the other, which allows us to focus on the relative index order rather than the values themselves. To efficiently solve the problem, we create a mapping of values from nums2 to their respective indices. This mapping allows us to transform nums1 into a new array, POS, where each element represents the index of the corresponding value from nums1 as it appears in nums2. This transformation is crucial, as it reduces the problem to verifying index order within a single array. For example, if nums1, I, corresponds to nums2, j, then POS, I, will be j. With the transformed array in hand, we turn to efficiently counting valid triplets. Instead of using a brute force approach, which would require checking all possible triplet combinations in O(n) cubed time, we use a Fenwick tree, also known as a binary index tree, bit. This data structure enables fast prefix sum and update operations, making it ideal for counting indices that satisfy the required constraints. We initialize two Fenwick trees, one to track the count of elements and another to calculate prefix sums of these counts, both of which will be used during the traversal of the POS array. With the Fenwick tree setup, we begin traversing the transformed array POS. For each element in POS, we use the Fenwick tree to count how many valid pairs, I, j, exist for the current index I. Specifically, we query the prefix sum to determine how many indices before the current one satisfy the relative ordering constraints. This gives us the count of valid, I, j, pairs for the current I. We then update the Fenwick tree to include the current index, ensuring that this index is considered for future queries. By repeating this process for all elements in POS, we calculate the total number of valid triplets, I, j, k, as we go. The key to the efficiency of this approach lies in the Fenwick tree, which allows us to perform both queries and updates in O log n time. This drastically reduces the overall complexity of the algorithm compared to a brute force solution. By the end of the traversal, we have the final count of all valid triplets that satisfy the constraints. To summarize the solution, we use two key data structures, a dictionary and a Fenwick tree. The dictionary, index_map, is used to map the values in nums2 to their indices, which allows us to transform nums1 into the relative position array POS. The Fenwick tree facilitates efficient counting and summing of indices during the traversal of POS. Together, these data structures enable an optimized algorithm with a time complexity of O, n log n. This is derived from the O, n, time required to create the mapping and the O, log n, operations performed for each of the n elements during traversal. The space complexity is also O, n, accounting for the dictionary and the Fenwick tree. This approach avoids the infeasible O, n cubed, complexity of brute force and demonstrates the power of combining mapping techniques with advanced data structures to solve problems efficiently. This solution to LeetCode problem number 2179, count good triplets in an array, optimizes the process using a combination of mappings and a data structure to handle sorted elements efficiently. Here's a detailed walkthrough of the approach. 1. Mapping indices *. The POS array is created to map the indices of elements in nums2 to their positions in nums1. This mapping allows us to transform nums1 into an array of indices based on nums2's order. 2. Transforming nums1 * using the POS array, we create a new array transformed where each element of nums1 is replaced by its corresponding index in nums2. This is crucial because it converts the problem into a numerical sequence analysis. 3. Counting good triplets *. The sorted list from the sorted containers module is used to maintain a dynamic sorted order of elements seen so far. For each element in transformed, we compute left_count, the number of elements in the sorted list smaller than the current element, using bisect_left. Right_count, the number of elements to the right of the current element, calculated as the difference between the current index I and left_count. The contribution to the total good triplets is the product of left_count and right_count. For updating sorted list * after calculating the counts for the current element, it is added to the sorted list to maintain the dynamic order for subsequent iterations. 5. Complexity *. The use of sorted list ensures that insertion and binary search operations are efficient, leading to an overall time complexity of O, n log n, where n is the length of the input arrays. This approach is efficient and leverages the properties of sorted data structures to handle the constraints of the problem effectively. It ensures that all possible good triplets are counted without resorting to a brute force solution, which would be computationally expensive for larger inputs. Here, we begin by importing the necessary utilities from Java and defining our solution class. The method goodTriplets takes two integer arrays, nums1 and nums2, as input. First, we determine the length of the arrays and initialize an array POS to map the indices of nums2 to their corresponding positions in nums1. This mapping is achieved by iterating through nums2 and recording the index of each value. Next, we create a transformed array, where each element of nums1 is replaced by its corresponding position in nums2 as per the POS mapping. This allows us to work with the relative order of elements in nums2. Finally, we initialize a tree set, which will help us maintain a sorted collection of elements, and a variable good triplets to count the valid triplets that meet the problem's conditions. The tree set is particularly useful here for efficiently counting elements smaller or larger than a given value. The loop continues by iterating through the transformed array. For each element, we calculate the number of elements smaller than the current value using the headset method of the tree set. This gives us the left count. The right count is derived by subtracting the left count from the current index, which represents all elements seen so far minus the smaller ones. The product of the left count and the right count is added to the good triplets variable, as it represents the total number of valid triplets with the current element as the middle value. After processing the current element, it is added to the tree set to update the sorted collection. Once the loop completes, the total count of good triplets is returned as an integer. This approach efficiently handles the counting process by leveraging the tree set for dynamic order maintenance and quick lookups. We start with the first example where nums1 is 0, 1, 2, and nums2 is 2, 0, 1. First, we initialize the variables. Nums1 and nums2 are given, and n, which represents the length of the arrays, is 3. We also create a position array, POS, of size n and initialize it to all zeros. Next, we map the indices of nums2 to the positions array. For each element in nums2, we set POS, nums2, I, to I. For example, when I is 0, nums2, 0, is 2, so POS, 2, becomes 0. Similarly, for I equals 1, nums2, 1, is 0, so POS, 0, is set to 1, and for I equals 2, nums2, 2, is 1, so POS, 1, becomes 2. At this point, POS is updated to 1, 2, 0. Finally, we transform nums1 into the indices in the order defined by nums2. By mapping each element of nums1 through the position array, we find the transformed array to be 1, 2, 0. This transformation will be critical for the next step. Now we proceed to count the good triplets using the transformed array 1, 2, 0. We start by initializing an empty sorted list, which will help us efficiently count elements less than or greater than the current one, and a counter good_triplets set to 0. We then iterate through the transformed array. For the first element, 1, there are no elements to its left or right, so both left_count and right_count are 0. We add 1 to the sorted list, which now becomes 1. For the second element, 2, there is one element smaller than it to the left, so left_count is 1. There are no elements greater than it to the right, so right_count is 0. We add 2 to the sorted list, updating it to 1, 2. For the third element, 0, there are no elements smaller than it to the left, so left_count is 0. There are 2 elements greater than it to the right, so right_count is 2. We add 0 to the sorted list, which now becomes 0, 1, 2. At the end of this process, no good triplets are found, so the total remains 0. The output for this example is therefore 0. In the second example, nums1 is 2, 0, 1, and nums2 is 1, 2, 0. We begin by initializing nums1 and nums2 as given, with n equal to 3, and the position array POS initialized to all zeros. Next, we map the indices of nums2 into the position array. For index I equals 0, nums2, 0, is 1, so POS, 1, becomes 0. For I equals 1, nums2, 1, is 2, so POS, 2, becomes 1. For I equals 2, nums2, 2, is 0, so POS, 0, becomes 2. The position array is now updated to 2, 0, 1. Using this POS array, we transform nums1. For each element of nums1, we map it to its corresponding position in nums2. So, the transformed array becomes 1, 2, 0. This transformed array is what we will use to count the good triplets. With the transformed array 1, 2, 0, we proceed to count the good triplets. We initialize an empty sorted list and set the good_triplets counter to 0. Iterating through the transformed array, for the first element, 1, there are no elements to its left or right, so both left_count and right_count are 0. We add 1 to the sorted list, which becomes 1. For the second element, 2, there is one element smaller than it to the left, so left_count is 1. There are no elements greater than it to the right, so right_count is 0. Adding 2 to the sorted list updates it to 1, 2. For the third element, 0, there are no elements smaller than it to the left, so left_count is 0. There are 2 elements greater than it to the right, so right_count is 2. Adding 0 to the sorted list updates it to 0, 1, 2. After iterating through all elements, no good triplets are found, so the total remains 0. The final output for this example is 0. In the third example, nums1 is 1, 0, 2, and nums2 is 2, 1, 0. We initialize nums1 and nums2 as given, with n equal to 3, and the position array POS set to 0, 0, 0. We then map the indices of nums2 into the position array. For I equals 0, nums2, 0, is 2, so POS, 2, becomes 0. For I equals 1, nums2, 1, is 1, so POS, 1, becomes 1. For I equals 2, nums2, 2, is 0, so POS, 0, becomes 2. The position array is now updated to 2, 1, 0. Using this POS array, we transform nums1 into the indices corresponding to nums2. For each element of nums1, we map it to its position in nums2 using the POS array. the transformed array becomes 1, 2, 0. This transformed array will guide the process of counting the good triplets. Using the transformed array 1, 2, 0, we count the good triplets. We initialize an empty sorted list and set the good_triplets counter to 0. Iterating through the array, for the first element, 1, there are no elements to its left or right, so both left_count and right_count are 0. Adding 1 to the sorted list updates it to 1. For the second element, 2, there is one element smaller than it to the left, so left_count is 1. There are no elements greater than it to the right, so right_count is 0. Adding 2 to the sorted list updates it to 1, 2. For the third element, 0, there are no elements smaller than it to the left, so left_count is 0. There are two elements greater than it to the right, so right_count is 2. Adding 0 to the sorted list updates it to 0, 1, 2. After processing all elements, no good triplets are identified, so the total remains 0. The output for this example is 0. Here, we analyze the time complexity of the solution. The overall complexity is O, n asterisk log n, where n represents the length of the input arrays, nums1 and nums2. Let's break this down step by step. First, we map the indices from nums2 to the order of nums1. This involves two operations, creating the POS array, which requires iterating over nums2, and transforming nums1 into the transformed array by iterating again. Both operations individually take O, n, giving us a total of O, n, for this step. Next, we focus on counting good triplets. The main loop iterates through all elements in the transformed array, which contributes O, n. Inside this loop, two key operations are performed using the sorted list data structure. The bisect_left method finds the insertion point for the current element, which takes O, log n, and adding the element to the list also takes O, log n. Together, each iteration of the loop requires O, log n, plus O, log n, equals O, log n. Since the loop runs n times, the total time complexity for this step becomes O, n asterisk log n. Now, we consider the final computation step. Summing up the contributions to the good_triplets count and returning the result is a constant time operation, O, 1. When we combine all the steps, the first step contributes O, n, the second step dominates with O, n asterisk log n, and the final step adds O, 1. Therefore, the overall time complexity is determined by the second step, which is O, n asterisk log n. Let's turn to space complexity. The solution requires O, n, space overall. First, the POS array stores the mapping of indices from nums2 to nums1, which takes O, n, space for n integers. Then, the transformed array stores the indices of nums1 in the order of nums2, also requiring O, n, space. Additionally, the sorted list object, which is used to dynamically maintain indices during the main loop, grows incrementally as elements are added. By the end of the process, it contains at most n elements, contributing another O, n, to the space complexity. Finally, variables like good_triplets, left_count, and right_count use constant space, or O, 1. When we add these components together, the total space complexity is O, n, from the POS array, O, n, from the transformed array, O, n, from the sorted list, and O, 1, from the other variables. Summing these values gives us a total space complexity of O, n. To better understand the efficiency of the optimized solution, let's compare it to a brute force approach. In a naive implementation, we would iterate over all possible triplets of indices, I, j, k, or I less than j less than k, checking each triplet against the conditions for a good triplet. This requires three nested loops, each iterating up to n, resulting in a time complexity of O, n cubed. The optimized solution, however, leverages the sorted list data structure to compute left_count and right_count efficiently. By avoiding redundant checks and using binary search for dynamic operations, we reduce the time complexity from O, n cubed, to O, n asterisk log n. The logarithmic factor arises from the internal balanced binary search tree of the sorted list, where each insertion or binary search takes O, log n. These operations are performed n times during the loop, confirming the total time complexity is O, n asterisk log n. The solution's space complexity of O, n, is derived from the arrays in the sorted list used for intermediate calculations, making it far more efficient than the brute force approach. When tackling this problem, there are several common pitfalls to watch out for. First, misunderstanding the constraints can be a big issue. It's not enough to just find triplets that meet the numerical conditions. Remember, the indices I, j, and k must also follow the strict ordering I less than j less than k. Skipping over this detail can lead to incorrect results. Another mistake is relying on an inefficient brute force approach, such as a triple nested loop. While this may work for small test cases, it will almost certainly fail on larger inputs due to time limit exceeded errors. Instead, you should focus on optimizing your solution, potentially using data structures like prefix sums or Fenwick trees. Additionally, problems involving multiple arrays often require careful index mapping. If you don't properly align indices between nums1 and nums2, you might introduce subtle logic errors. Overcomplicating your solution is another frequent issue. Sometimes, a simpler algorithm like sorting or hashing can solve the problem more effectively than a complex structure like a Fenwick tree. Lastly, edge cases are critical. Arrays with duplicate values, very small arrays, or constraints pushed to their limits, such as an input size of 10,000, need to be tested to ensure your solution accounts for all scenarios. Now, let's consider how this problem connects with interview scenarios. One key skill being tested is your ability to recognize patterns in combinatorial counting and find ways to reduce the search space efficiently. This often involves tools like prefix sums, binary index trees, or sorting. It's also important to communicate your choices clearly, explain why you're choosing a particular approach, and discuss its trade-offs. For instance, while a Fenwick tree may offer faster performance for certain operations, it's more complex to implement, and interviewers will appreciate hearing your reasoning. You should also practice relating this problem to others with similar patterns. Follow-up questions in interviews often explore related concepts, so being able to identify overlaps can give you an edge. Finally, optimization is a big focus here. Demonstrating how you can reduce the time complexity from O, n cubed, to something like O, n squared log n, or O, n squared, using smarter approaches will help you stand out. Highlighting these improvements shows not only your technical skills but also your ability to think critically about efficiency. This problem is closely related to several others that involve counting under specific conditions. For example, LeetCode number 315, count of smaller numbers after self, requires counting elements with similar constraints and can be approached with Fenwick trees or merge sort. Another is LeetCode number 493, reverse pairs, which involves optimization techniques like segment trees to handle counting efficiently. Then there's LeetCode number 1395, count number of teams, which also deals with combinatorial constraints for valid triplets, and LeetCode number 327, count of range sum, which uses range-based counting with prefix sums and divide and conquer strategies. In terms of alternative approaches, Fenwick trees or binary index trees are excellent tools for efficiently counting and updating frequencies, bringing the complexity down to O, n squared log n. Sorting combined with binary search can also help quickly locate valid indices, offering a simpler implementation. Two-pointer techniques can be effective in specific variations of this problem, especially when paired with sorting to narrow down the search space. However, remember that more advanced structures like Fenwick or segment trees, while efficient, do increase the complexity of implementation. Simpler methods, like sorting or prefix sums, might be easier to debug and explain in a high-pressure interview setting, so choose your approach wisely based on the context. Great job! We've successfully tackled the problem count good triplets in an array. In this conclusion, we summarized our approach, key takeaways, and the complexity analysis. If you found this helpful, remember to like, subscribe, and continue practicing. See you in the next video. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!